All right, we are recording. So, this is our exercise book for Chapter 5. And I told you yesterday you could get started on the 5.1 to 5.3 assignment. Let me just give you some hints on how to get going for number 1 and number 3. So let's start with number 1. We would like to graph sine theta over the interval from negative 360 to positive 360. So I didn't do any yesterday where I worked in degrees. So let's do it in degrees. Okay, so I would like to graph sine theta in degrees. All right, so I would use graph paper if I had it. If I didn't, I'd just try to work fairly neatly on loose leaf. And I'm going to need an x-axis. So let me get an x-axis going here. I will grab a line, and I should probably put this in tablet mode. And okay, so let's put the x-axis, say, right here. There we go. There's my x-axis. Okay, so let's put a y-axis down while we're at it. And here's my y-axis. Okay, if I was just working with paper and pencil, I'd do that with a ruler. Okay, now, what do I want on here? I want to go from negative 360 to positive 360. So what would be a smart thing to count in? Well, the points I'm going to put on my graph tend to be the points I know, which would be my 30-degree family, my 60-degree family, and my 45-degree family. Oh, and of course my 90s. And if I were to count in 15-degree chunks, I would hit all of those numbers, because 15 goes into 30, it goes into 60, it goes into 45. So I'm going to count in 15-degree chunks. So this is 15, there's 30 degrees. 45, 60 degrees. And then, so this will be 15, 30, 45, 60, 75. There's 90. So 1, 2, 3, 4, 5, and then the sixth place is 90. So 1, 2, 3, 4, 5, and the sixth place is 180. And I just realized this isn't going to fit, is it? Well, let's see. Can I make that? Let me see if I can make this work. I guess I could count by 30s and then have half places for the 45 family. I should have counted this out first. Why can't I make this longer? What if I click on it here? Oh, I has the power. I'll just make this longer. And I'll go to the other side and make it longer. And then I'll just do that. There we go. Okay, so 90, 180, 1, 2, 3, 4, 5, 270, 1, 2, 3, 4, 5, positive 360. And then 1, 2, 3, 4, 5, 90, 1, 2, 3, 4, 5, 180, 1, 2, 3, 4, 5, 270, and 1, 2, 3, 4, 5, negative 360. Look at that. It's almost like I just knew that was the size I should make it. It exactly fits. And again, I can grab that with my mouse and just stretch it over. There we go. There. Okay, so I think I'm ready to start graphing. What do I know? Oh, I guess I got to pick a scale. So this is my theta, and this is my sine theta scales, or axes. And okay, I guess I need a scale for the y-axis. Well, sine is only going to go up as high as 1 and as low as negative 1, right? I mean, that's all it's going to do. So count in 0.1s maybe? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. There's 1. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. There's negative 1. All right. What is the sine of 30 degrees? 1/2. So at the 30-degree line, 0.1, 2, 3, 4, first dot. See how I did that? What do I know next? I know the 45 degrees, which is actually the very next dot here, right? Because it's 30 plus 15 is 45. And sine of 45 degrees is root 2 over 2, which with a quick calculation I know is, I shouldn't say equal to 0.7, I should say is approximately equal to 0.7. So this one's going to be 0.5, 0.6, 0.7. Any questions on how I got that? Well, I guess I could have started at the sine of 0 is 0. And then what is the sine of 60 degrees, which is, this is 30, this is 45, this is 60. That's root 3 over 2. So what's root 3 over 2's decimal? I think it's 0.86. Oh, there I am saying it's equal again. It's approximately 0.866, so around 0.9. So at the next, I go up to that was 0.7, 0.8, 0.9, but like just under it. This almost looks linear, but it's not. This is definitely a curve. And then the 90-degree mark has a sine of 1. And then from there, the hard work is kind of done, because I know there's symmetry from going around the unit circle, right? I know that after 90, you have 15 and then 30, then you're in the 30 family right here, and I'd be this point again. And then at the 45 family, I'd be back down to this point again. And then at the next one, I'd be back at this point again, right? Or in other words, 0.866, 0.707, 0.5. And then, so this was 90. So I might not, well, maybe I better put some numbers there. There's 90 degrees. This was 180. That's where I hit 0 again. And then this, I might as well make the graph here if you want. I can connect the dots. Try to make a nice smooth curve. Oh, okay, my hand got a little bit lousy on that one. Small eraser. There we go. What do you think? Get the idea? All right. What happens when I go 30 degrees past 180, 210? Well, then I get to 1/2, but it's negative. So 0.1, 2, 3, 4, 5. And then at the 45 family, I get to that 0.7, 0.6, 0.7. And then at the 60 degree family, I get to the 0.86 or 0.86 or 0.87, so I'm rounding that to 0.9. So that's 0.7, 0.8, 0.9. Then I get down to -1, which is this -1? I think so. Yep. And then I go back again. All right. Skip a spot, 15 degrees, then 30, then 45, then 60, then back to 0. Oops, don't like that one. And do not put an arrow at the end on that right dot. How come? Why would I have to take off a half mark if I put an arrow in there? Why do they force me to be so evil? What's wrong? What are you thinking? Yep. Yeah, it actually tells us that there's a range for this graph. Well, actually, I guess technically there's a domain for this graph. Those are my x values, so that's the domain. But you get the idea, right? You're not supposed to graph past that, okay? So there you go. All right, and then the other side is just basically going to be the mirror image. So 0.1, 2, 3, 4, 5, 30 degrees. Oh, what? Oh, jeez. Sorry, I had the eraser on. 0.1, 2, 3, 4, 5, and then 30 degrees. 6, 7 at 45 degrees. And 8, 9 at that one. And then move over 2 spots and you get to -1. There we go. And then move over 2 more spots. And you should be at that point. And then move over another spot. 8, 7, 6, 5, 0. At this point, I'm just counting. What? What happened? Oh, you know what's wrong? Is my wrist touched the screen in a different place than I was drawing. That's what happened. There we go. I'm pretty happy with this. This one looks quite a lot more professional than the bicycle wheel one that I did on the board. And then, okay, let's see. At negative 270, I'm back to 1, right? So there's 1 at 270, and then again, move over 2, and you're at the 0.9. Move over 1, 2, you're at the 0.9, and then the down 2 from there, 0.7, and then 6, 5. So there's the 5, and then over 1, and that's the 0.7 and the 0.5. There we go. There. Any questions on how I made that? All right. So now, from there, let's see. What would I do for number 2? Oh, I guess there's other questions here. Identify the exact value of the function when x is 225 degrees. So let's see. Where is that? That's 180 plus 15 is 205 plus 15 is 220. So it's somewhere around here, and then you could just read it off the graph. Okay? So I would read that off the graph. Is that good? Okay? And then what else do they ask you to do? Determine the X-intercept, so that's pretty easy. You can just read them. Okay? All right. Okay, you get the basic idea. For doing number 2, instead of counting, I could actually count the same way if you wanted to. For number 2, I could make the exact same grid that I've made here, but just change these into radians. And I was kind of making this point yesterday as we were running out of time. If I counted this in radians, I can use the exact same grid, but now every one of these is a 12th of pi, right? Because that's pi by 6, and that would be pi by 3. Pi by 4 would be in the middle, right? Because it'd be 3/12 is 1/4. So 12ths are actually the same thing as 15-degree chunks, and they're actually quite easy to make a grid with. I don't always make a grid this detailed. Kind of depends on what I'm doing. All right, and the only one on here that asks you to do any translations here are 4 and 5. So what would I do with number 4? If I was using the same grid, what would I do with number 4? Well, for number 4, I'd have to extend my grid up this way because it has a translation, it has a translation of +2, which means that it's going to move up. This is 0, 1. So this point would move up another 10 spots and be up here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 2, and then 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. There's 3. So I just have the same graph. I just have to move everything up. Oh, and it's a cosine graph, so it would start here, or its peak would be here. So give yourself some room to practice those. The other thing, of course, is this one doesn't shift the graph up, it actually stretches it up. So again, I'd have to make my grid go up and down higher, like I did there, and in this case lower, because it would go up and down 4 times as high as this point and 4 times as low as that point. Okay? And again, I don't mind if when you're doing your homework, especially as you get kind of used to this, if you use Desmos to kind of give yourself, I guess I want a new graph here. Oops. Just give me a new graph. There we go. If you're just learning, if you're just, still kind of feeling your way out on how to do these things, use Desmos to help you out. So you have y equals, let's see, so it's sine theta x, whatever, and then so that's your graph, And then, of course, you can ask it, you can change its x-axis and its y-axis. Right now, this is clearly in radians, but switch it to degrees. Now you're probably going, hey, where did the graph go? Oh, well, obviously, if that's 1 degree, 2 degrees, you're not going to see much of the graph happening here. But if you change this so that, again, your x-axis goes from negative 360 to positive 360, and you ask it to count in steps of 15 degrees, you get the exact same graph that we had. And of course, you can do whatever you want with the y-axis. So what was number 4 again? I think you're graphing y equals 4 times sine x. There we go. Notice what changed about it? Did its x-axis values change? Nope. Still 360, 180, and 0. It just stretched. Okay, so you're going to have to get some practice doing those. And for today's lesson, let's start in on doing more transformations and translations than that. So let's go to the notes booklet, and let's go to the 5.2 lesson. And where do we go? There we go. Part 1. All right. Do these letters look familiar? A, B, C, and D. Each one represents a transformation just like they did back in Unit 1. So, what transformations do they represent? Well, A, we actually already talked about A the other day. A is amplitude. It's how much you stretch the graph or compress it. B is not period itself, but period is 2 pi divided by b, or 360 degrees divided by b, depending on what whether you're in radians or degrees when you graph it. C is, just like it was before, my horizontal shift. And D is what we call our vertical shift. But I can kind of expand on these two definitions of horizontal shift and vertical shift. I can kind of call, first of all, the horizontal shift is usually in trigonometry called phase shift. And it gives the graph a starting point. Vertical shift is what we're now going to call the central axis. There's a procedure to drawing these graphs, and you do it as follows. So for example, we want to sketch the graph of y equals 3 sine of 2x minus 2 pi over 3, close brackets, plus 2. Just like in chapter 1, the first thing we have to do is turn it into this form, which means we have to do a quick factoring. And now it's in this form, because now I can tell you that, yep, no problem. A is equal to 3. B is equal to this 2 here. C is equal to pi by 3. Notice it's not negative because there's a minus in the formula. So that's a shift to the right, the way it was back in Unit 1. And D is equal to 2. Okay, so next, I think of what my y equals sine x looks like. Also remember, that's also called the parent function, the function that we're going to use to kind of figure out how to change things. So what does sine look like? Well, again, it starts at 0. It goes up, down, and back. That's 2 pi. This is pi. That's pi by 2. That's 3 pi by 2. And then, of course, it goes down, up, and back. Once again, that's negative pi, negative 2 pi. You get the idea. So I recall what that looks like. And I ignore the fact that one of my lumps is kind of pointier than it should be. And too high. And now that I've seen it, I can't ignore it. I have to fix it. Sorry. Try to make it look like that one. Get the idea. Okay, next. You determine the values of A, B, and C. So again, I wrote them over there. I kind of forgot that we already have them coming. So A is 3, B is 2, C is pi by 3. Sorry, wait a minute. Isn't pi 2 pi by 3? Oh, no, we factored it, right? It's pi by 3. And D is 2. And then we do the transformations in this order. D, A, C, B. Step 1, find the vertical displacement, and that tells me my new horizontal axis. In other words, it tells me how much to shift the graph up and down. So in this case, D is 2, so my new central axis will happen at 2. So instead of my graph going up and down from here, don't draw that, it's going to go up and down based on this being the center. Okay? But I'm not ready to draw yet. I just need to find where my vertical axis is. Then, next I do A, amplitude. So starting with, again, my horizontal axis being along here. So this is my new axis. Amplitude is how high and low the peaks and valleys go from that horizontal line. So if A is 3, I have to go up 1, 2, 3, and this represents my maximum height. This is how tall the peaks are going to go, and they can't go any higher. Conversely, I can go down 1, 2, 3, and this is how low the valleys can go. So this is my minimum. I know that I won't cross that line. So this is my distance here. That A distance is 3, and this A distance is 3. Those should look like the same distance. Again, it's very hard to draw straight lines across the page. You could use a ruler if you wanted to. And then my phase shift, my C number, is going to tell me where to start the graph. So my phase shift is pi by 3, and of course it's a positive, so that means to the right. So instead of starting my graph here at 0, and by starting I mean, starting my crests and troughs, I'm actually now going to start over here at pi by 3. That's where my sort of starting point for the graph is going to be, except I'm not going to be on this line. I'm going to be up 3. So let's put everything together on our next one. But first, we have to find the period. So period, I know that b is equal to 2, and that period follows this formula. Period is 2 pi divided by the absolute value of b. I guess I could put that in absolute value brackets, which is 2 pi over 2, which is pi. Now a normal sine curve needs 2 pi to make an entire wave. One up and one down and back is 2 pi of distance, right? But this question is going to be kind of squooshed together, right? It's going to be shorter from left to right. I think we're ready to graph everything. Put it all together. And what does it spell? Here we go. So this pi tells me that, again, maybe I should put this in words. One full cycle completes in pi units. But again, I'm going to say starting at pi by 3. Why starting at pi by 3? Because that's my horizontal shift. So I think I'm ready to graph now. I'm going to graph here, let's see. I'm going to count by, I think again I'll count by maybe 12ths just to get started. So 1 12th, 2 12ths, 3 12ths. There's pi by 3. So 1, 2, 3, 4 12ths, 5, 6, 7, 8, 9, 10, 11, 12. And then that'd be 13, 14, 15. Now, why is 15 pi by 12 an important number to me in this graph? Because it represents where the first cycle should end. Get what I'm thinking? I'm thinking if I start at pi by 3 and I have to end after 1 pi units, I have to end somewhere between there and there. I have to start here and end there. Okay, while I'm at it, let's put the other things on the graph that we did. So what was the displacement again, or the d value? The d value is 2. So 1, 2. This is my axis that we go up and down from. And there's my starting point for the graph. So my starting point is at pi by 3, 2 units up, which means that this end point will also be there. And now I'm just going to, first of all, figure out how high and low my graph goes. So how high and low does my graph go again? Oh yeah, its amplitude is 3. So I go up 1, 2, 3. And I go down 1, 2, 3. My little graph label is going to be in the way a little bit there. And those two lines that I just drew tell me how high and low the graph's going to go. And it says now the last step is to plot the 5 main points. I've just plotted 2 of them. The 5 main points are, for 1 full cycle, the 5 main points are start, end, max, min, and node. I'll bet everybody knows what all those words mean except maybe node. Physics students, what's a nodal point on a wave? Have you guys done waves in physics yet? Oh, that's the one they gave you to do on your own. Okay. Well, it's where you go back to the starting point, but you're not done a cycle yet. So the nodal point actually I could maybe do right now, because the nodal point is going to be where? The nodal point is going to be exactly halfway between these two things. Now this is pi by 3. This is pi. So this would be pi plus a pi by 3. So what's a pi plus a pi by 3? This would be 4 pi by 3. Let's find the node. How do you find halfway between two things? Exactly. Add them together and divide by 2. Pi by 3 plus 4 pi by 3 is 5 pi by 3, but I'm dividing them by 2, so that is 5 pi by 6. Okay, what was I counting in? 12ths? So if I was counting in 12ths, 5 pi by 6 is 10 pi by 12ths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Halfway. If that doesn't look like halfway to you, it's because I was drawing without a ruler and I didn't estimate very good. But according to my counting, that's where halfway should be. Where should the maximum be? Well, normally, so this is my node calculation. Normally, where is the maximum? Where's the first maximum on a sine graph normally? It hits 1 when it's pi by 2, right? But I have moved over pi by 3. I guarantee you somebody's going to try doing this and they're going to get 2 pi over 5. And that's just, and somewhere your grade 7 teacher will feel a chill go down their spine. How do you add fractions? What do you need to add fractions? You need a common denominator. So this is 3 pi by 6 plus 2 pi by 6, which is 5 pi by 6. Oh, hang on a sec. Is the max, do I have the maximum in the wrong place? Where is the normal? Oh, wait a minute, sorry. Normally that's where my maximum is, but oh yeah, that's right. Our period changed, right. So it's actually 5 pi by 6, but divided by 2 because we have half the space normal. So it's actually going to be this 5 pi divided by 12. You know, you could have also just taken this point and the starting point, added them and divided by 2. But let's see. 1, 2, 3, 4, 5. So 5 by, hang on, 5 pi by 12. No, that's not right. It should be 7, shouldn't it?
Yeah.
What have I done wrong? Where's my mistake in my work here? I don't know. You know what? Let's just do it the right way. Oh, hang on. I want to erase a lot of things at once. I'm going to do that. Haha. Okay, so the maximum should be halfway between this dot here and this dot here. So what is halfway between 5 pi by 3, or sorry, by pi by 3 and 5 pi by 6? There we go. Now I'm going to use my common denominator of sixths. Yeah, this is working. It's 7. I don't know what I was thinking wrong the first time. But there we go. 5 pi by 6, add 2 pi by 6 is 7 pi by 6. But I'm dividing that by 2, so it's 7 pi by 12. There we go. So 1, 2, 3, 4, 5, 6, 7. So I'm going to hit my max right about there. Where should my minimum be? Well, my minimum should be halfway between the 5 pi by 6 and the end point, which was 4 pi by 3. So that's going to be 5 pi by 6 plus 8 pi by 6 divided by 2, which is 13 pi by 6 divided by 2, which is 13 pi by 12. So let's count to 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right down there. And I have now made one complete crest and trough of my graph. Oops, I don't like that line. Oops, now I erased too much of it. There we go, I like that. There we go. Now, did it say where I wanted to graph? It just wanted to graph, let's see, what am I graphing? Let me go back to the original question here. I am graphing this. Now, it doesn't say that there's a restriction on the domain anywhere. So you know what I should do with this graph? I should put arrows on it, because it does go forever. And if I was feeling ambitious, I could just keep counting, right? 1, 2, 3, 4 units from here, or I should say, yeah, 4 units and I get to here. So, and then 1, 2, 3 units and I get to there. So I could just go 3 more units this way and I'd get to the next peak, and then the next node, and then the next minimum. So maximum, minimum, I could just keep drawing this as long as I wanted. It's just a matter of counting the 12ths. Okay? So there we go. There's your first example of these kind of graphs, and we have to draw them. Let's put together a little summary of what it looks like when you sketch these. How did I find the central axis? It's the D number. That's all it is. How did I find the amplitude? It's the absolute value of A. How did I find the period number? It's 2 pi divided by the absolute value of the B number, or 360 degrees divided by the absolute value of the B number, depending on whether you're graphing in radians or not. And if you're wondering, what's with all these absolute values? The negatives don't tell you anything about the size of how high or low the max and mins go. It doesn't tell you where to shift or stretch anything. Guess what negatives tell you? It tells you the same thing it did in chapter 1. It tells you reflections. We'll look at that in a sec. Phase shift is C. Maximum is my D plus A. And of course, I just showed you to figure out horizontally where your maximum is. Just take the horizontal C value and your nodal point and just add them and divide by 2. And to get the nodal point, add the period number to the phase shift number and divide by 2. Your minimum is D minus A. And the range of this graph will always go from the minimum to the maximum. All right. Let's try a couple more. I'm going to switch colors. I'm going to switch to black. Had enough green today. All right, this one's already factored for me. So let's see. And this one has a negative on it. So that means, let's take a look at Desmos and make sure that this makes sense to us. If we have the graph y equals sine x, what's going to change about it if I put a negative in front of it? Get it? It reflects in the x-axis, which is the same thing the negative did in front of A back when we were doing Unit 1. Make sense? Reflection, reflection, reflection. If I had a negative in here, what would change about the graph, you think? Whoa, isn't that interesting? Let's get rid of this negative, see if this makes sense. Notice that a negative in front here and a negative there have the same effect on the graph. Why is that? Because reflecting in the x-axis and reflecting in the y-axis actually ends up being the same thing. Can you kind of see that? Like take this point right here that I'm pointing at and reflect it in the x-axis. Boom, there it is. Take this point here and reflect it in the y-axis. Isn't that interesting? So if I put a negative in front of there, actually cancel those two things out. Well, that's neat. Okay, anyway. Let's see if we can graph this thing. Okay, let's follow our steps. Step 1, let's figure out what all of our values are here. A is 3. B, I should say the absolute value of A, but you get the idea. B is pi by 2, C is 1, and D is -2. Okay, what did it tell us to do first? It told us to do the D value thing first. So I'm going to, so the D value is -2. So, D value is -2 and A is 3. So I have to go down and count down to -5 to fit this graph on. So -1, -2, -3, -4, -5. Please notice I'm freehanding this, so that's going to make my sketches very sketchy at best. So there's my minimum kind of barrier. Here is my new central axis. And then go up 3 units from the central axis. 1, 2, 3. So this is my max, this is my min, and this is my central axis. Where's my starting place? My starting place is at 1. Okay, I'm in radians because of the pi here, so I'm going to start at 1. Now, that's interesting because it's not like Not like I'm shifting by pi by 6 or pi by 3, which is easy to count. You mean to me that I got to actually count along here 1, 2, 3, 4, 5, 6? Yeah, I do. And actually, this is kind of cool. It's actually going to be easy to do that because the b value has a pi in it. You see, the period is this formula, 2 pi over the absolute value of b. Well, if b has a pi in it, it cancels the pi's, and I can count the period in whole numbers. So when you see a b value with a pi in it, it actually makes the graph easier to make. 2 pi divided by the fraction pi by 2 times by the reciprocal cancels the pi's. And I can just count to 4. And I know that I do a complete period in 4 units, 4 radians. So I can just count by whole numbers of radians. I don't even have to split them into pi's. So I'll count 1, 2, 3, 4. I'll count, say, 5 in each direction here. 1, 2, 3, 4, 5. I could have maybe spread that out a little. 1, 2, 3, 4, 5. Good enough. And I now know that I normally would start a sine curve here, but I'm shifting 1 unit to the right, so I'm starting my sine curve. Oh, and 2 units down, so I'm starting my sine curve right here. And I just realized that's too far to the left. There we go. That's better. There's my starting point. So let's now make the rest of our 5 important points. What's the next important point? The end point. How do I find it? It's 4 units over. 1, 2, 3, 4. There we go. End point. Oh, and I could go this way too. 1, 2, 3, 4. There. There's 2 waves. I need to make an entire wave from here to here. Let's find the node. Remember how much work I had to do with fractions and pi's, and I goofed it up on my first try? How easy is it to find the halfway point between 1 and 4? 1 plus 4 divided by 2 is 2.5. Beautiful. 1, 2.5. There's my node. Boy, did I ever draw that badly. This distance from here to here should be the same as from here to here. 1, and then it has a period of 1, 2, 3, 4. Oh, wait a minute. Hang on. I just realized I've goofed this up again. Can I have a mulligan on that? Sorry, guys. That's why this looks wrong. It is wrong.
Sorry, I'm writing in pen.
Why are you doing notes in pen?
Because I want my pen.
You're some sort of psychopath. Okay, so anyway.
So many mistakes in there. Do you have any whiteout?
Actually, I do have whiteout.
Oh,
You're lucky. I actually normally don't carry whiteout, but there we go. I don't know. This hasn't been used in a while. It may have dried up. There you go. Anyway. Okay, sorry. The period is 4, and I'm sorry. I started at 1, which means its final endpoint should be 5, which it is. And I had that in the right place. This is the one I have in the wrong place. And what's the halfway point between 1 and 5, not 1 and 4? Duh. So the node is going to be halfway between 1 and 5. So 1 plus 5 is 6. 6 divided by 5 is 3. 1, 2, 3. There we go. It's even easier than I thought it was. Okay. Where will its maximum be? Well, its maximum will be halfway between 1 and 3. But wait a minute. Where does this maximum go? It goes over here. Why does it go over there? Who can tell me why it goes over there? Dum, dum, dum. We're reflecting it in the x-axis. Normally a sine curve starts by going up and going down, but this negative means that it's going to start by going down and then going up. Ha-ha! So there we go. So we're going to go down, and halfway between 1 and 3 is 2. And there we go. Okay, to make this purdy now, let's connect our dots. And again, we weren't told that there was a restriction on domain, so it goes on forever. And since we have all kinds of room, why don't we make another crest and trough? So all I got to do is count, right? There's a start and an end, which means the node's in the middle. So 1, 2, right in the middle. And that means that it's going to hit its next crest here and hit its next trough here. And there we go. And I mean, I could just keep counting all day. It's actually really nice when the B value has a pi in it. It makes for much easier counting. You don't have to count in fractions of pi or in groups of 15 or 30 degrees or whatever. Okay, so there's our second example. Let's try to get through one more here. I've given you a lot of information. How are we doing? Anybody have any questions? All right. Let's get these out of the way. Kind of just scrap ideas here. Okay, so there we go. So that's, I guess I should label my graph. This is X. This is Y. And I guess I probably should at least show that that's 1 so that you can tell that that's 1 and that this is also, you know, -1, or that that's up there, that's 1. There, good enough. That's all the labeling you need. All right, this one will be harder. B is not a number with a pi in it. So, first things first, the D value is 3. The A value is 4. That means we have to start by counting, we have to go 3 and 4. We have to go up at least 7. You get how I got the 7? I know that the graph is centered on 3, and it goes up 4 from there. So 1, 2, 3, 4, 5, 6, 7. Might as well go down 7 while I'm at it. 1, 2, 3, 4, 5, 6, 7. Although I won't need to go that far down in the graph. In fact, I'll only really need to go down to -1. All right, and let's see. What do we want to count by this time? We're in radians, so we're going to count our B value this time is 2, which means that the period is 2 pi divided by 2, which is pi. So I'm going to finish an entire crest and trough in pi units. We can count in maybe quarters of pi. How about that? Let's count in quarters of pi. You know why I'm counting in quarters of pi? Why do you think I decided to count in quarters of pi? Because that's how much I got to shift by. So my shift, or my starting point, careful, I'm starting on the left this time, right? Because C is a negative. So I might as well count in quarters of pi. So 1 quarters, 2 quarters, 3 quarters, pi. 1 quarters, 2 quarters, 3 quarters, 2 pi's. And we got to go backwards too. 1 quarters, 2 quarters, 3 quarters, -pi. 1 quarters, 2 quarters, 3 quarters, -2 pi. Good enough. All right. Let's put in all of our information. D is 3. 1, 2, 3. A is 4. So my maximum is up here at 7. And, oh, that's kind of trending downward, but you get the idea. And counting down 4 from here gets me to -1. So here's my minimum. All right, starting point is 1/4 pi to the left. But wait a minute. This is a cosine graph. If I was drawing a regular parent function cosine graph, what do you know about the starting point here on the y-axis?
Starting point is the maximum.
The starting point's the maximum this time. So this is going to have a maximum right here. In a cosine graph, start point is a maximum. Okay, so that means to get to the next maximum, I do it in a period of pi. So how many places is pi? Well, I'm in quarters of pi, right? So 1, 2, 3, 4. There's my next maximum. Let's do another one. 1, 2, 3, 4. There's my next maximum. Where's my minimum? Well, my minimum is halfway between this and this. So count. You can just count it with your fingers if you want to. Right there. Oh, wait, sorry, down here. My bad. Oh, hang on, I'll just get that point out of there. That's not supposed to be there. There we go. There's my minimum. And my nodal point will be halfway between my maximum and my minimum, which is there, and there. I think I'm ready to draw my first. There we go. And while we're at it, let's draw a few more. Maximum, node, minimum, node, maximum. I kind of squished those together a little bit. You get the idea. Ugh, I don't like that line. I don't like that one either, but I'll stick with it. Let's go this way. So node, maximum, node, minimum, node. And once I get bored, I just put arrows and say, we're done. And I ignore the fact that a couple of them got way too pointy. It is just a sketch. So let's kind of look at the properties of this graph. You can say that, this graph completes one cycle in pi units. It starts, and I keep putting quotations around the word starts because, a graph that's infinite doesn't really have a starting point. It starts at negative pi by 4 at its maximum because it's a cosine graph, and ends one cycle at 3 pi by 4. Get it? Pi units to the right. So this was why don't I just use a highlighter? My starting point was right here. My ending point was right here. And then from there, I just counted everything else. So I could say that my maximums happened at negative pi by 4 and 3 pi by 4. I could say that my minimums happened at pi by 4, right there. And the next one would be 5 pi by 4. I should say maybe etc. And of course, my nodes happened at 0 and pi by 2. And you get the idea. There you go. Guess what these things take? They take practice. That's really all there is to it. You really aren't going to say, oh, I was paying good attention to this class and it all made sense to me. When the test comes, I'll be really good at it. No, you won't. You really have to kind of work your way through this. This is a very different skill than you've probably ever done graphing before. So it takes practice. You really have to work through these. So the first 5.2 assignment, you can get started on it. We'll do the second kind of part of 5.2 tomorrow, but we won't even finish the second part of 5.2 tomorrow. And then I'm thinking that gives you a couple of days there during the whole wellness break where we won't have class, where you can just work on both of the 5.2 pages. So I don't expect you to finish all the 5.2 tonight. I don't even expect you to finish the 5.1 and 5.3 questions tonight. But I'm going to get through the rest of the lesson tomorrow so that you can kind of work on all of it during the wellness break and over the weekend. Okay, so there we go. I'll stop the video. If anybody has any questions, I can take questions. Thanks for watching.